hope everyone will follow suit. Okay, thank you. Our next speaker is Ms. Janine Schoombie, who will be presenting on computational insights into wind patterns and Albatross mortality. Did I pronounce the surname?
Yes, it's perfect. Thank
you.
You.
Okay,
Awesome.
thank you.
Thanks.
Yes.
I just need to check if I actually typed my surname correctly. That was done very quickly, and that would have been embarrassing. Good morning, everyone. I am really privileged to have been asked to come and talk here. It was really fun compiling this presentation. It's really refreshing to be able to talk about the computational side of my research, so that was really fun. Thanks. Okay, so the work that I'll be talking about mostly was part of my PhD research, and then there's some extra work in there that preempted some of this work, and so the main crux was I was looking into wind causing albatross crash landings, which often resulted in fatalities. Did this thing change? Am I not talking loud enough? I feel like it's echoey. Is it fine? Okay. Where's the thing? Okay. Okay, just so you know what to expect, I'm going to try and stick to the time, but I'm going to run through a quick background on the wind side of the project, and then I'll go through some of the albatross aerodynamics, and then focus on some of the computational stuff, and then very quickly go through some of the study results, hopefully, and then discuss some more of the computing things. And then I feel like I had to add the one extra slide on one of the buzzwords that have been going around through the conference. So. Okay, a lot of my work has been done on Marion Island. For those of you who don't know where it is, it's about 1,700 kilometers south of where we are. This harbor is actually the closest harbor to Marion Island, and it's about halfway to Antarctica. So it's very cold, and it's very windy, and it rains every single day. And it's also what we call a hyperoceanic climate, so it experiences gale force winds most of the time. Every day, it will be gale force at some point. Maybe not all day, but I remember there was this one day where we didn't have wind, like there was one. And I remember it vividly. Okay, so because of the wind, the ecosystem is what we call the wind-molded ecosystem. And so the biologists on the island really wanted to know how do the wind patterns change within the island, and how does that shape the vegetation, and how the vegetation changes from one side of the island to the other. And then when you look at the available data, the finest scale data that we could find in terms of wind vectors was about a 25 by 25 grid. And Marion Island falls inside that grid. At its widest is about 22 kilometers. So I propose that we do a computational fluid dynamics analysis of the entire island. It is one of the biggest islands that have been... simulating an entire island is not new, but this is one of the biggest ones that have been done. So I'll explain a bit on CFD and how we use that in a second. Yeah. Next. Okay, so we also deployed 17 wind stations all around the island. Each station had 2 sonic anemometers. Sonic anemometers, no moving parts because maintenance. And then some of this data was used as inputs to the computational fluid dynamics model, and then some of the data was used to validate the model afterwards as well. And it also gave us a bit of a time scale. So we've been recording data since 2018. So we have a nice big data set of wind all around the island. And the reason we need to do all around the island is there's only one wind station on the island at the moment, and it's in the lee of the island. So it doesn't give us the full picture. The people who've been to Marion Island, a lot of the times we always talk about 4 seasons in a day, where when you're at base, it's nice and sunny. When you're on the other side of the island, it's windy and it's rainy and it's awful. So the people who walk there and traverse the island know that the weather changes a lot depending on where you are, but we don't have the data to prove this. Okay, so just for those of you who are not familiar with computational fluid dynamics, basically what we do is we're simulating flow over a geometry, and usually it's a very complex geometry. And so what we do is we define a volume of, in this case, air around a geometry, and that volume is broken up into tiny little cells. And then what you do is at the boundary of your volume, what we call it the flow domain. You will define your, in this case, a wind vector, and then from your boundaries, you will calculate the wind vectors and the pressure and the temperature and all kinds of variables at each cell as you go, and it's an iterative process. So it could take anything between 2,000 to 10,000 iterations to get a converged solution. And this is a cross-section of Marion Island for that simulation. Okay, so the wind was simulated over Marion Island for 16 wind conditions, 16 cardinal wind directions, and 1 speed. So the surface resolution of this model was 30 meters resolution at the surface of the island, so a much finer scale than what we had before. But the domain was also really, really wide, so we were working with a really low speed. Then you need to push out your boundaries really far away from the solid model that you're trying to model to make sure that the boundaries don't mathematically interfere with the end result. And then his simulations, it was a master's student, Kyle, I don't know if I said that, okay, who did the simulations. So his simulations, he ran on the maximum amount of nodes for the normal queue, and each simulation ran about 5 hours, but the big issue was that his simulations, he had to cap his simulation size, so he had to choose which variables he saved. So if I go back, at each one of these cells, you can, in some software, you can choose how many variables you store. So there's this long list of things that you can store, including different turbulence properties and all kinds of things. And he had to cancel out a lot of that to cap his simulations at 125 gigs. So we can't even open these files on a local machine. We can't even open the file without the CHPC. And he used ANSYS Fluent to do his simulations, which is one of the 2 really popular commercial software to do CFD in. And so what we've got out, this is just an example of one of the wind directions, the westerly wind. So what we can see is a nice fine scale resolution here. So we can see the red is where the wind accelerates over all the little small peaks on the island, and we can see a nice low speed separation behind all of the, in the lee of all of the large landforms on the eastern side. And that, in that nice bubble there, that's where the weather station is. So hopefully you can see where the problem is. But the area that I was interested in for my PhD is this area here at the bottom. So that's called Santa Rosa Valley, and this ridge over there is called Gray-headed Albatross Ridge. And that's because it's home to a really big colony of gray-headed albatrosses. These are cliff nesting birds, and in 2017, the ornithologists on the island, so there in that corner there, that's a little bit of Santa Rosa Valley, they found adult albatrosses stranded in the valley. And because I was the only aerodynamicist in a 2,000 kilometer radius, they said, why? So the hypothesis initially was that this might be due to some wind conditions, some kind of flow phenomena that's happening over the ridge. But the first thing we had to do is first find out, is this happening at a large enough scale for it to be a problem? So the first thing we did was we did some field observations first. We zigzagged up and down the valley and counted a bunch of carcasses to try and see where there's a concentration of crash sites. And then I also sat and watched birds for months. I feel like I got paid to sit and watch albatrosses fly. I have nothing to complain about in life. And then the other thing was I knew I was going to have to do a lot of computational work because I couldn't find any aerodynamic information to supplement all of my hypotheses in literature. So, and the best way to get aerodynamic information of any kind of aircraft or anything is to do, well, we either do wind tunnel tests or we do CFD. And in wind tunnel testing, you're limited physically by the capabilities of the wind tunnel and also the space of the wind tunnel. And so because I wasn't sure what their limitations were, you want to simulate as much as possible. So wind coming from many different angles, side slip angles, angles of attack, and then also different air speeds. And I knew the best way to do that was computationally. So I had to also get a geometry of the bird, which also didn't exist. That was 3 years of the 4-year PhD, by the way, but I'm not going to talk about that too much. And then once I had the geometry, I could carry on doing my simulations. The only reason the simulations were quicker than the geometry part is because I had the CHPC. I feel like I should put that in. Okay, this is just to show you quickly what my geometry looked like and just a comparison to the real thing. Okay, so now I had a geometry and I can go to my CFD software and I define my volume around the body of the Albatross. The software I used was Star CCM+. Star CCM+ and ANSYS in terms of solvers are pretty much the same thing, but this is the one that I'm used to. That's usually where it ends up, is just the one that you're more familiar with. So the other thing, so what I mentioned before was you put boundaries around your domain. And so when you're doing computational fluid dynamics, if you don't have a validation study, you have to make sure that what you're computing is trustworthy. And as I also said, your boundaries can be too close to the thing that you're modeling and the geometry that you're modeling. So what we do is we call a domain dependence study. So what we do is we put the domain boundaries as further and further and further and further away from the geometry, and we check our results. And when we get to a point where the results don't change anymore, we have a result that is independent of the domain size. And then the next step is to look at the mesh. So when you're breaking up your volume into all the little small cells, which is your mesh, theoretically, the more cells or the smaller the size of the cells, the more accurate your simulation should be, but you can only go so fine until you run out of computational resources. So then we do a mesh dependence study. So you make it finer and finer and finer and finer again, and then when you don't see a change in your results anymore, you have a result that is independent of the mesh. And then another thing that's interesting, and this makes CFD different than some of the atmospheric modeling and also some of the MD modeling that the health science people do, is we don't necessarily simulate time. There are some flows that can be steady, so a time averaged simulation is sometimes good enough to capture a system, but it's always good to check. So I did a temporal convergence check. So what I did was I did a steady simulation and then I did an unsteady simulation. But also when you're doing an unsteady simulation, your time step is also really critical, and that could also influence your results. So then you change the time step and you make it smaller and smaller and smaller, and you check the difference in your results. So this is just to show, this is my temporal convergence study. And the finest, or the smallest time scale, which is really the standard for how you should be doing this, it would have taken 5 days per simulation if I maxed out the number of nodes on the normal queue. And I already knew I had to do a lot of simulations, so this was not feasible. But luckily, I saw a very small difference in my results, so it just made sense to do a steady state simulation for all of my simulations going forward. Okay. So this is just a very brief breakdown of all of the simulations that I had to do, just to give you a picture of how computationally intensive this can be. So as you'll see, there's a mesh convergence twice, because as it goes with CFD, it's an iterative process in itself when you're solving, but it's also iterative in the sense that you're going to build the mesh and find a mistake, and then you have to rebuild the mesh, and then you find a mistake, and then you rebuild the mesh, and then you find a mistake until you're happy with it. And it's also very important once you do your simulation to inspect your flow field and compare to similar things to make sure that you haven't made a mistake somewhere, because keyboard errors are fairly common. And you make sure that you get all of that out of the system before you go and you produce your final results. So I redid my mesh convergence twice. The second time was just to double check, so I didn't do all of them. And then there was the temporal convergence, which took too long, so there was multiple iterations of that. There are all kinds of different solvers and things that you can do, but I'm not going to go into too much of that. And then I started doing my simulations, and then I found an issue in the mesh, which is when I went back to there, and then I had to redo some of them, and then I found an issue in the solver, and then I had to go back. But the final data set that I eventually used comprised only 170 simulations. I say only, it is a lot, and that is not standard necessarily for the kind of, this kind of analysis. It's just because I really wanted to go very broad. So I ended up actually, it's probably more than 500 simulations that I ended up doing, but just the summary of everything that I only did on the gray-headed Albatross simulations was about 455 simulations. So that is a lot. And then also when I started with some of the first simulations, there's a parameter in the software that you can check how long does it take per iteration that you simulate. And from there I can extrapolate how long it'll take to do the whole simulation and how long it is going to take to do all my 170 simulations. And when I started with the normal queue, I calculated that it would take almost 3 months to do all of my simulations. But now this was luckily at the beginning of the whole process, and now I know how it goes. I'm probably going to find a mistake, and I can't wait 3 months, go back, redo something, and then wait 3 months again, and it would just take too long. So very panicked, emailed Charles, please can I have access to the large queue? Otherwise I'm not going to make my deadlines. So I'm really, really grateful that they gave me access to the large queue, which gave me access to 50 nodes. And that brought my computation time down to 10 days, which was very useful. Otherwise, I would still be doing CFD today. And then I did a quick scaling check. I didn't go, I think, just correct me, how many nodes can you really check out with a large queue? It's 100, right? Yeah, I didn't go up to 100 mainly because if I went past 50, my chances of picking up a faulty node were too high. So I would pick up a faulty node and the simulations would take much longer than it would, even if I had waited in the queue for the normal queue and waited for the simulations for the normal queue. So the waiting time with the large queue was also a lot less than with the normal queue. But then when you pick up this faulty node, everything goes downhill from there. So there's quite a wide range when you're working with a large queue. And the simulation time, there was quite a big range. But there was also, the simulations would sometimes fall over, but I think that was something, that was a software specific thing. Okay, thanks. Okay, quickly, 5 minutes, I have to run through some results. Okay, so basically, back to the crash landings. So these contours here in the middle show where the most crash landings occurred, and you would see this coincided with lots of like really swirly, turbulent airflow in the lee of these interior peaks and also in the lee of this ridge. And then, sorry, I'm just going to skip that. Okay, and then when I looked at the lift of the Albatross when I did my aerodynamic study, what I found mostly was that they are really, really good at producing lift. They can produce lift up to 9 times their weight, which is really high for a bird, even in really strong downdrafts, which was really interesting. So even at negative angles of attack, they can generate lift above their weight so they can maintain gliding. And there's this really interesting efficiency curve, which I still need to figure out why it's so sharp. That's not normal. Okay, so basically what it boiled down to was that the main causes of crash landings were mainly loss of lift when they fly through these pockets of low air or low wind, where they have a loss of lift and they are forced to land. Sometimes those landings can be soft landings in the valley. But then when they're flying through this swirling wind in the lee of this ridge, they are very likely to encounter strong side winds and downdrafts, and it's always a combination. So they can generate enough lift with a strong side wind and a strong downforce, but not both. And this happens, what's interesting that it happens in the dominant wind direction. Okay, some positives. The software that I use, StarCCM Plus, is really, really easy to use on the CHPC, because the CHPC does not have to buy a license to have the software. It's a sort of a pay-as-you-go system where the university pays for the license and they give you a code and you can easily write that in your job on the CHPC. And that was really, really easy to use, so I was never capped on the amount of processes that I could use. And then also the access to the large queue really made all the difference. And so I will be Dr. Schoombie soon. And then some of the issues, this is a little embarrassing to admit, especially given yesterday afternoon session, but I lost all except 6 of my 170 simulations because I did not make the purge deadline. So very, very important to learn from my mistakes and back up backup. Have a good backup system in place when you start. My files are really big, so I was putting off zipping, because just zipping the files you needed to check out a node, and that became a lot of admin, and I was busy writing up the PhD. So don't leave it to the end. Have your system in place beforehand so that as you do your simulations that it's zipped and it's transferred and it's backed up. So use all the systems that are in place. And then obviously the unreliability of the large queue is a minor issue. And I think probably now, because we're getting a new fancy cluster, I think this is hopefully going to be solved soon. So yes, very much looking forward to the new upgrade. And then just to quickly touch on the GPU thing. So when we're doing fluid dynamics, in my industry, people always say, oh, we just make pretty pictures. But making visualizations of the flow is a really important part of fluid dynamics. So when we're doing computational fluid dynamics, it's always important to have a really strong GPU purely for the visualizations. But recently that has changed. So now the software, especially StarCCM+, I'm not really sure about the other software to be honest, but StarCCM+ has slowly rolled out some of their solvers to be able to use them on a GPU. This year is the first year that the solver that I use for the external aerodynamics can be used on GPU, so I still have to try that out, but that is definitely the future. At this year's conference, they really, really pushed hard that we should be using GPUs, not CPUs. So I feel like I just had to slide that in there as well. Okay, that's me. Thank you so much.